Welcome to this presentation on Smith predictor for deterministic systems. We will motivate and design it. We will present an example and Scilab code. Consider a plant model with delay of k units. We recall some facts that we have already seen. Unless the input has an instantaneous effect, output will have a non-zero delay. Since this is impossible, there is bound to be some, however small, delay. Input and output measurements are synchronized. As a result, a non-zero delay results in at least one sample delay in sampled data systems. So this k is in general greater or equal to 1. Let us consider a paper machine model taken from Astrom's book. The references are given in the textbook. So we will consider the performance of a 2-DOF pole placement controller with and without delay. Without delay means there will be z power minus 1, that is the absolute minimum. With delay means with z power minus 3 here. We would want the closed loop characteristic polynomial to be 1 minus 0.5 z inverse as done by Astrom. We can specify directly in our pole placement controller. We also want tracking of steps. As a result, include delta as internal model. In solving the Aryabhata's identity, we get S1 and R1 as given here. Here is the Scilab code delay.sce. It uses pp_im, which was presented earlier. After execution, run this delay_param.sce that sets up parameters for xcos and invokes the xcos model given here. Its screenshot is here. On execution, we get the plant output for paper machine for the no delay system, that is with z power minus 1 here as thin line. With z power minus 3, you get the response as given here. You can see the response with delay is just a delayed version of the system without the delay. For both of these, the input is the same. The control effort is the same for both cases. Now let us discuss how to implement this formally, delay compensation. So let us start with the general delay of k, where b is a polynomial in z inverse, and we will also assume b naught to be not equal to 0. Let us write the same transfer function gz as z minus k minus 1 with one delay included in bd. So if I substitute this here, multiply it out, you will get this equation. As I mentioned earlier, one delay is included in bd to denote minimum unit delay. It also prevents algebraic loops. Now we come to Smith predictor. So let us use the definition we had in the previous slide, and we propose an estimate. Start with the plant model, that is yn, plus add a few more things. What is that? You add this here using km, bdm and am, which are estimates of k, bd and a. If we know them well, that is if km, bdm and am are identical to k, bd and a respectively, you can see that the second term here will cancel this term here, leaving only this, because this will multiply 1 here. So we will get this, which will be the delay free version of the original model. So as I mentioned earlier, the first term is yn with exact knowledge. The estimate is seen to be this, which is the original model with only 1 unit delay. It is as if you go inside the plant and locate the response before the delay and pull it out for control purposes. So here I have written it as y hat of n. Previously we had used y hat of n given up to n minus 1. It does not matter, all we need is that it is an estimate. The interpretation is y hat is delay less estimate of y. Now let us see what happens to the Smith predictor with 2-DOF controller. This is the delay less plant's output as given by this estimate, and it can be written schematically as follows. So you can see that this is the original plant with BD including 1 delay and 1 less here. Input is U, output is Y, and then in parallel we also take this output and then add the two, call it y hat. Now the estimate, that is the delayless estimate of y, is fed to S naught. Remember, this is our 2-DOF configuration. So R naught, S naught, T naught form the 2-DOF controller for the plant with output y hat. So what is the closed loop polynomial? Let us calculate it. This is the estimate for y, we call it y hat. Let us simplify it. The 2-DOF controller is given by our standard Aryabhata's identity, except that we have now y hat in the place of y. Let us substitute y hat in this and we can calculate u to be this. This y hat also has a term containing u, so you have to bring it to this side, simplify it, you get this expression. I will let you do this and make sure that you get this right. So this is the equation that we obtained in the previous slide. Recall the plant output. Now let us substitute for this y into this, that is we close the loop and we get this expression. And there is a small mistake in the textbook, you may need to correct it. You can see the expression for the characteristic polynomial to be as given here. I would want you to check this also. So this is the characteristic polynomial for the Smith predictor using the 2-DOF pole placement controller. Now there are some simplifications possible if we assume that we know the plant exactly. That is, if AM equals A, BDM equals BD and KM equals K and KM equals K, you can see immediately that this term will cancel this term. As a result, we get phi CL equals A into AM R naught plus this term multiplying 1, because this term would have cancelled this term, and we have replaced BDM as BD, and of course we already substituted AM equals A and KM equals K to get this term cancelled. Notice that in phi CL A appears explicitly. As a result, the closed loop is stable only for open loop stable systems, that is A by itself has to have its zeros inside the unit circle. The textbook discusses a method for unstable plants. So if you are interested, you may want to check the book. There are some limitations for the Smith predictor. It works well when the delay is known exactly. If the delay is not known well exactly, then the performance deteriorates. Nevertheless, it is a useful tool for control engineers. Smith predictor is also the starting point for internal model controllers to be discussed subsequently. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.